back to task. First 2 weeks, Maxwell-Boltzmann. What we're doing is we're calculating the velocity of a gas. The point of this is that you learn the true nature of statistics in the process. That's why I have this coin. We're going to talk about flipping a coin, which is going to sound boring, and then I'm going to blow your head off with something incredibly simple that shows you don't have any idea how this works. That's the whole point. All right, so anyway, so the name of the subject is Maxwell-Boltzmann distributions. Now this is the subject of the next 2 weeks. After this, we get into quantum mechanics, and then we have graduation. That's pretty much how it goes. Most of the class is on quantum, and it's plenty hard. It's very mathematical, right? So I warned you. Yeah, I know I said this to you last time, right? In thermo, you can, oh, well, how much energy does it take to make a car go down the street? Right? You kind of have some intuitive sense how that works. When it comes to this stuff, you truly don't. So that's why you have to be reliant on your ability to do the math to answer the questions. You are reliant on it. Because half the time, the answers are like H bar 1 or 0. And the thing about quantum is it doesn't make sense. I mean, there's no folksy analogy. Oh, it's like when the cat scratches scratches me or something, or when the car drives down the street. There's no folksy analogies for this. That's why it's like considered like, wow, it's a thing because of that. That describes everything. That's also cool. So anyway, so that's quantum. Maxwell-Boltzmann is a good warm-up. Again, it's very mathematical. And there's some quantum mechanical concepts that I'll get to probably at the end of the lecture. You're going to start to see the quantum mechanics is starting to show up in this stuff. This is also about statistics. Quantum mechanics is actually a statistical, the mathematics is based on statistics. Now the mathematics is also based on second order differential equations, right? Those are about the most hideous things you can solve in a math class. This is a math plus chemistry class, so it is unpleasant. I warned you that. So, quantum mechanics is statistics plus second order differential equations. Anyway, we're there in 2 weeks. Statistics, distributions, let's cover that. And where's my coin? Sorry, I'm all out of order. It's been a while, right? Okay. Heads, tails. Oh, it's an eagle. Anyway, and then there's a head. Oh, Statue of Liberty. Okay, so I flip it. Someone call it. Heads. It's a tail. Okay, it's a tail. What were the odds of that? 50-50. Okay, now I'm going to flip it again. What are the odds of another tail? 2 tails. What are the odds? 50%. And it would be wrong. It's a head, so you're wrong. No, it's pretty. Okay, now that shows you. Now this isn't the trick, by the way. Every time I flip the coin, the odds are 50-50. Now where I tricked you, a lot of you said 25%, but you actually didn't get it right. The reason was because the tail, the first tail, had been predetermined. That's because I flipped it after the fact. It is already predetermined that that was the first toss. When I tossed it again, it was still 50-50, heads or tails. What you were thinking of was before I made the first toss. If I said to you before I made the first toss, what are the odds of 2 tails? Then 25%, right? So let's write that down. Again, hopefully this is kind of stupid easy, and I swear I'm going to blow your head off here in a second. This is actually the most fun lecture of this class just because of this. Okay, so now you know enough statistics to know the way to do this. I know I had statistics like combinatorial permutation, combinatorial mathematics in high school. I don't know that I had it in college, but anyway, I remember some of this stuff. So we know that the way to figure out, in a very crude sense, probabilities is to put down all the options, and then you see all of the possibilities, and then you look at the number of occurrences that is corresponds to what you're asking. So in this case, 2 flips of a coin. There's 4 outcomes. We were interested in tail over 4. There's only one of these therefore the probability, percent probability was 0.25. Sorry, that's 1 over 4 is 0.25. And I want to make sure that you're all okay with remembering that, right. 1.0 is 100%, 0.25 is 25%, anyway. Okay, blah, 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 blah. Remember, the trick was that I had to ask the question before I did the first toss. After the second toss, it was still 50-50. That's a little nuance, and it does give a lot of people. That's kind of a good intro. Okay, so let me stop there. You think you know how a coin works. Now I'm going to put this in a completely different context. Now, this is a molecule, and you're an experimentalist, and you're going to do experiments on the molecule, and it's in a little vacuum chamber. All right, now the damnedest thing is people can do single molecule experiments. We can look at single molecules. We have equipment that can do that. It takes various forms. There's like a microscope. There's a scanning probe deal that look at single molecules. That's like a really sharp point that just pokes the molecule. All these instruments are about $500,000 at the bare minimum. Again, we have 2 of them here. It's kind of incredible. These are very, 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 very new. For the most part, when you're interacting with chemicals or when you are doing experiments on chemicals, you are, let's say we're going to do gas molecules, they're in a chamber. You generally put these at low pressure so that the molecules don't collide with each other. You don't want that happening. It kind of can confuse things. You just want to study the individual molecule. So I have a chamber. It's about this big. It has to be big enough for me to hold. It has to be big enough for me to align a laser through it. And I try to put the pressure low so that the molecules are not hitting each other. And there's about 10 to the 15 of these in here. And here's my point. You think you understand the flip of a coin, but when you're flipping 10 to the 15 coins, everything you know is now wrong. And I'm going to show you how spectacularly how wrong that is. So I've got some coin molecules. We're going to do spectra on them. We're going to press a button and do the experiment, and the outcome is the number of heads. Right now, what I need to know is the nature of the molecule, which is that it's two-sided and they're equal. Now, to know that, I have to see an equal probability of the head and the tail. So if I have 2 of these, I need to see a head and the tail and the tail and the head. If I see that, then I have perfect information. Okay, now, we can already see a bit of a problem when I have 2 molecules in the chamber. We're going to look at this one. 2 molecules in the chamber. I have these 2 that give me that result. These 2 tell me that the molecules, the 2 molecules, are composed of 2 sides and they're equal. Half the time I do the experiments, let's say I do like 10 experiments or something, half the time, so 5, I get tail, tail, and head, which screw it up. All right, but, if we're smart enough, we see half the time we get heads, tails, tails, heads. It leads us to the conclusion that while all of our data, only half our data, support the idea that this is a coin with 2 equal sides, if I look at half my data and say, well, that's what I think is happening, you can actually use it then to explain the outliers, right? Right, it kind of makes sense. Yeah, it's kind of, if you're thinking like this is some kind of trick, it's not. This is the part that's simple. Right, so I'm doing spectra. I have 2 molecules in the chamber, and half the time I see heads, tails, tails, heads. I figured out that it's 2-sided, the 2 sides are equal, and that actually explains why occasionally I actually see different results than what I expect. It's perfect. All right, so now you think you understand probability. This is where we go off the rails. Now what I'm going to do is I used the computer last night to start modeling more gas molecules, more coin molecules, and I did up to 100,000, and I didn't even get to a mole, for which is it's going to be obvious why. So let's look at the probability of the 50-50 split. Okay. Now again, I want to see a 50-50 split. For 2, I want to see tail, head, or head, tail. We're not going to worry about the order. Tail, head, head, tail tells me that this is a 2-sided molecule. Half the time I get that. Fine, we just talked about that. 4 coin molecules in the chamber. Remember, we actually have like 10 to the 15 or so. The odds of getting tail, tail, head, 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 tail, anyway, there's actually 6 permutations. there's only a 37.5% chance. So do 100 experiments and 38 of the times, you'll see this even split. So you're less sure. Okay, you know that there's two sides, but let's say that you're tail heavy. You're going to think that this molecule is asymmetric. So you're getting it wrong. That's the point. Okay, now again, I cannot study 4 molecules in a gas chamber. It's just impossible. I mean, I just can't do it. Let's just go to 100, 7.96%, that I would get 50 heads, 50 tails. Again, let's say that it's heads heavy. I do some experiments on 100 molecules. I see more heads. I assume that it's asymmetric and that the head side is bigger than the tail, which is wrong. Let's do 1,000. It's now 2.5%. Let's do 10,000. Actually, I had to use a computer to simulate this at this point. The formulas for these things don't work anymore. And 100,000. So put 100,000 coin molecules. I do the experiments, and I say, what's the probability that I get exactly 50,000 heads, 50,000 tails that correctly reveal the two-sided, the even two-sided nature? That happens 0.0026% of the time. Basically never. Now, what are the odds? If I do a mole, if I'm looking at a mole of a gas, which you remember, that's kind of a large balloon. It'd be like a balloon about this size. What do you think the probability of observing half a mole of heads, half a mole of tails? And I mean exactly half. Right, it's obvious, right? 0. You will not observe that. You will assume that the coin molecules are asymmetric. And they are not. So that 50-50 coin toss thing is now completely screwing you. It's leading you to the wrong conclusion. Completely. Which is like, what the hell, right? Okay. What's wrong? What do you think is wrong? It's kind of obvious, right? Remember I said, if you're going to say that the molecule is completely symmetric, the heads and tails are exactly even, which they are, I need exactly an even split. I need exactly half a mole, 3.1, I don't know, whatever the number is, down to the last significant figure. What's wrong?
You're only taking it one time point, not an average?
Well, not average. I mean, no. I am averaging. These are the results. The problem is that, okay, let me give you another one. A car's going down the street. All right, you drove here. You're going 50 miles an hour. Where are you going? Were any of you going 50 miles an hour? Just someone say yes, okay?
Yes.
Yes, okay. You were going 50 miles an hour. Now hold on. Were you going 50 miles an hour, or were you going 50.0000000000000? Were you going exactly 50 miles an hour? No. See, the problem is I'm being too specific. Of course, when I flip 10,000 coins, 100,000 coins, what are the odds that, I mean exactly, I don't mean sort of half, I mean exactly half. None. Well, sorry, it's 0.3%. See, the problem is that the question is ridiculous. I'm not thinking about this correctly. I'm thinking too absolute. And because of the large number of observables, the large number of molecules, the nature of the coin is starting to obscure itself because I'm not thinking about it correctly. I'm not thinking about the statistics correctly. So now we have to correct that. All right, now here's how you do it. Now the answer, by the way, is to give yourself a spread. It's not 500,000. If you have 100,000, I'm not asking for 50,000 heads, 50,000 tails. I'm going to give myself some wiggle room. I'm going to say, what are the odds that I get 50,000 heads plus or minus some wiggle room? Actually, let me back up a bit. And I'm going to wipe out these guys because they're small numbers. We want to work with large numbers because that's where there's a problem. So what I'm going to do is I'm going to add a spread. And I'm going to look at that as a percent. Okay. Now, if I do 100 coins, and I do this experiment on 100 coins, I want to see 50 plus or minus 3. Here, so 3 over 50, by the way, is 6%. So that's in the percent sense. Okay. Now remember, 3 over 50 is 6%. You know that. Okay. The odds of that So this is the probability of a 50-50 split plus or minus the spread. Okay, now what this means is I'm observing 100 molecules. How often, and I'll do the experiment a zillion times, how often do I observe between 47 and 53 heads? Right, you got me there? How often do I observe not a perfect even split, but close to perfect, within 3 of 50-50, or 6% of 50-50? The answer is 51.7% of the time. I see. This is revealing the two-sided nature of the coin. The even two-sided nature of the coin is not coming out here. In fact, that's getting completely lost. Now you guess where I'm going with this. Now, the spread on 1,000 has to be a little higher, plus or minus 10. If I say that I need to see between 490 and 510 heads, and by the way, 10 over that number of 500 is 2%. I observe that 51.3% of the time. Right, you see, just like my analogy with the car, you're never going exactly 50 miles an hour. You're going 49 to 51 miles an hour. Okay, 10,000. Now I think you see how to play this game. I'm just going to finish it up for the hell of it. So the spread, the number gets bigger, but as a percent it gets smaller. That's why I'm including both of these numbers. You know, if I have more molecules, I need a wider spread, but as a percent of 30 over 5,000 is 0.6%. And this happens 50.2% of the time. And notice the trend here is that I'm getting closer and closer to 50%. Exactly 50%, like 50.0000%. Okay, 100,000, I need to see 50,000 plus or minus 105. That's 0.21%. Notice again that the spread percents are dropping, and the likelihood that I observe that within the spread is basically now 50%, and go on and on and on. So, if I get down to a mole, the probability of observing a 50-50 split is 0. That's ridiculous. I'll have a certain spread, and if I allow myself to say, I'll observe heads or tail, I'll observe half heads within a certain spread, I'll get 50%, and now I can see the correct nature of this coin. I'm now making the correct interpretation. For those of you who are a little bit more mathematical, I'm going to include a graph of this. So this is for 10K tosses. What I did was I histogrammed the results of, this is the number of heads. And again, remember that the point of this is that it's absurd to think that you're going to get exactly 50-50. You're going to see a certain spread. Now the area under this curve is exactly 1.0. And I'm just trying to remind you how statistics works, by the way. Again, this is the probability of having a certain number of heads tossed out of 10K. So obviously on average you get 5,000. But you see that there's a reasonable spread of about 100. If you look at the area under that, it's 1.0. That means that, the way to interpret that, by the way, if I give you this graph on the exam, here's the probability and the area under the curve is 1. What does that mean? You say, if I toss a coin a bunch of times, I will certainly get some number. I'm going to have some value for the number of heads. Of course you will. Maybe it's even 0. It's just improbable. But that's what that means. It's very simple. Okay, now if you look at plus or minus 30, which is about here to here, the area in this range, and again, this is the spread, this is the plus or minus, I'm doing 10K, right? Plus or minus 30, that's this width here. This area is 0.5 or 50%. So there you go. All right. Now again, I know this question.
How do you go about getting the spread? Is that the standard deviation of the Gaussian curve?
Actually, what I can do is, the statistics of coin flips are pretty well known. I can solve this analytically. I know the formulas for that. I actually did this, the formulas for all these statistics get a little dodgy when you get to 50,000 to 100,000, it's a little dodgy, so I actually had to do a Monte Carlo simulation on the computer to get these results here, so they may be a little off. What I did was, this is a bell-shaped Gaussian type curve, and the formula for it is well known, but I just ran a simulation and captured this to see what the spreads were. Now the reason that it's not, why is it not 50? Why is it not exactly 50? I mean, I can just adjust the width here to be exactly 50. The reason is because I wanted a whole number. If I wanted this to be 50, I would just make this 2.97, right? Make the spread a little narrower, but that's not a whole number. So you see why that's a little funky? Okay. And as I get more and more, I have more, basically I have more significant figures on the spread, and that's why these numbers become more sensible as you get larger and larger. So that man knows his stats. Anyway, okay, so we're going to be looking at a lot of curves, so let's get used to that. Okay, so point of this is when you have a large number of observations, probability fails, but this probability with a spread succeeds. You need to work with this, can't put this 0 and drop this 0. Drop this and go with this. So now you have to learn about this. This, by the way, is called, this is a probability density. Called a probability density. So forget probabilities. Probabilities no longer work in this class, probability densities. Let me show you some examples of probability densities and do a little math to show you how they work. There's a cool little aspect about this that is the reason I'm doing all this. Okay, so now we've got to know about probability densities and what the heck is that. And ultimately what we do next class is we're going to apply this mathematical analysis towards the speed of a gas. It's all just, again, an introduction to quantum mechanics. That's the whole point. Okay. Probability density, how does it work? I'll show that in a minute, but what I want it to do is to make sense to me. It makes sense to me when it turns into a probability, right? When you're telling me that this coin has a 50-50 chance of being a heads or tails, when you tell me it's exactly 50% heads, 50% tails, when I can mathematically analyze it correctly, I know the microscopic nature of the molecule. I see it perfectly. This is what we want to do in physical chemistry. We don't want equations with wiggle signs, this is sort of equal. We don't do that. It's equal. I need to know exactly what this molecule is, not sort of what the molecule is. I want to know that it's exactly even-sided. Now again, as a person, I can only understand probability. Let me use some shorthand. I understand probability, I understand it quite well. But as I just blabbered, I can't use that anymore because it doesn't work. Instead, I have this probability density. So I'm going to call it that, probability density. Now let me introduce, I'm just going to throw this at you. This is how it works. You're going to multiply it by a spread. I'm going to call this y. Y will be a property. I'm using very traditional language. Sometimes this is the probability density. Sometimes you'll see there's the letter F, but I don't like throwing too many letters at you, so I'm not going to do that. Anyway, traditional to call this an F in the property of y. Anyway, okay, so there's some property times the probability density gives me the thing I understand. I understand this. I understand the spread. We just talked about heads or tails. Your car plus or minus, 50 plus or minus a mile an hour. That makes sense. Probability that you're going exactly 50 miles an hour. That's a nonsense question because the answer is 0. Okay, so this gives me what I understand. This is easy to understand. So what the heck is that? What the heck is that? Well, that'll be next lecture. But now we have to go further with this. Okay, probability spread. Now, do you see as a percent, what's the trend? As we get closer and closer to a mole of molecules, which is what we're always observing, the probability spread gets lower. Now, okay, so now it's turning to like 0.06, 0.02. Again, I'm using, numbers for probability. 0.006. When I get to a mole, what is the number? It's what? And then again, so look at the percent, right? Because it's all relative, right? So the spread is getting smaller. It's getting very small. When I get to a mole, zero. Okay, well I have a mathematical symbol for zero. Oh. Yes, it's a partial. What do we do with partials? Integrate them. Right now you got an integral. Okay, so probability densities, and that would be what I drew up there, that bell-shaped curve, times a partial. When you integrate it, gives you a probability. Okay, remember partials? Just in case you forgot, I know we got some new people in here. I haven't forgotten you. Partials, they have units. Don't forget that. Now, this is where I want to stop talking about coin tosses because that's not what I'm supposed to be talking about at all, said the cat. And there's also, I don't know what the unit is of a toss, so that's a little weird. Their value is of course zero. That's why they have to be integrated. Oh, let me write that down. So therefore, must be integrated. Let me use some shorthand there again. Okay, so they must be integrated because otherwise, this is zero. This is zero. Look at this probability distribution. Let's look at the probability distribution. Hopefully we'll understand this a little bit better. Okay, what is the probability of measuring, again, exactly 5,000?
Zero.
Well, now in 10 it was technically 0.8%. But now let's say that this was a mole, and of course it was zero. It's zero, right? If this was actually a mole, it would be zero. Now, if we give ourselves a spread, then it's not a ridiculous question, and the answer is what? The area. It's the area. It depends on the spread, by the way. Now, I know I led you to think that, so let me make the spread about like I drew it before. If I make the spread wide enough, then it's about 50%. Right, as I drew here, I'm trying to draw it to use that question.
Wait, so you're saying as the spread decreases as we approach 1 mole, what would be zero?
No. I'm just trying to emphasize is that if this is for 1 mole, if you don't have a spread and you ask for the 50, what are the odds of exactly a mole over 2 heads? Heads or tails, we'll just choose heads. The answer is 0. You will not observe exactly half a mole head, half a mole tail if you do a mole of coin flips. You will not observe that. That's ridiculous. There's too many other outcomes. You have to give it a finite spread. Finite. Now, hopefully your gut tells you, and I'm telling you, even if your gut doesn't tell you, the probability is an area. Cha-ching! There's a lower limit. Now the lower limit and the upper limit are whatever you choose it to be. Now if you apply it to those problems I put up there, since I intentionally sought, since I did all this on my computer, I intentionally made certain that I knew what the correct spread was to make that area 0.5, 50%. So I manipulated this chart so that I would be able to demonstrate that anyway. So, okay, let's stick with 50K. Let's say for the 100K toss where we want to see 50K, the lower limit would be 5,000 minus 30, 4,970 and 5030. Okay, and this would equal what? It's right up there. 5029 technically. That is what my computer got. Okay, so now the point is that now you're seeing how you do this, how this game works. With the probability density, you integrate over some range and you get a result. Okay, now what if I did this? What's this answer? You should be able to do this. 1.0. Oh. There you go. So that's how this game works. With that, let me go ahead and tell you a little bit more about where we're going, but I'm kind of finished up. This is normally about as far as I normally get. Let me tell you a little bit more about where we're going next lecture. Next lecture is going to be rough for certain because remember that time I wrote, I think it only happened once last semester where I wrote an equation that went across the board. Yeah, that's going to be like every day. Was it a joke? That literally every day we're going to be writing an equation that goes across the board. I told you the class is a bit harder. Okay. And what we're going to do is we're going to apply what you just learned towards velocity of gases because it's just a good introduction to Maxwell-Boltzmann is about probability densities of velocities. It's a great way to learn statistics, which we then apply to quant. That's the goal. Okay, now what we're going to apply all of this towards is what's called the Boltzmann distribution. Okay, the Boltzmann distribution is the probability density of energy. So, the name of the game is, you see the rules of the game, you have to get a probability density times the spread. Unfortunately, the nature of the spread requires an integral, and the output is the probability. You understand probabilities, you kind of understand integrals, hopefully you do understand integrals. Probability density, that is the thing you have to get to. Sometimes it's easy, sometimes it's a nightmare. This is kind of intermediate. Okay, Boltzmann he actually figured out that formula for entropy, if you remember that last semester. He has two famous formulas. There's the entropy formula you saw last semester. I showed you that briefly. But he also figured out how nature distributes energy, which was kind of astounding, right? The way to think of this is, let's forget coins. Let's talk about molecules now. So I still got my vacuum chamber, but there's molecules and I'm not coin molecules or whatever. And they have a certain energy. What is the probability that they have a certain energy? That is the question. And then that would be the probability density. Okay, now don't write this down. I'm going to intentionally mess this up. Let me be very specific. Let me say that there's a very particular energy. It's a kilojoule. Okay. And don't write this down. Don't write this down. I'll explain why in a second. If we were doing coin tosses, this would be the formula. It would be the energy divided by all possible energies. That would be the answer. Just like 2 heads was 1 out of 4 possibilities. 25%. 2 coins, 2 heads, 25%, because that's 1 result out of possible 4. That's how coins work. That is not how nature deals energy. It just doesn't. So someone actually analyzed what would happen if nature did things this way that you're kind of used to with like coin tosses. It turns out neither mass nor energy would be conserved. So remember there's 3-4 fundamental laws. Energy is conserved, mass is conserved, angular momentum is conserved, the speed of light is conserved, and you're blowing 2 of them. What he figured out, now there's a derivation to do this, but it's incredibly painful. Nature uses exponentials for whatever reason. Now again, it can be derived, but it would take all lecture. I don't want to do it. I just want you to trust me that nature deals energy by some probability function. This is the probability function. This is it. Except there's a problem. E to the joules. Does that work? Gotta be unitless. Gotta be unitless, remember? Remember that, don't write this down, but remember this, that you can write this as a Taylor series? You remember last semester, the first day I told you that any expression in physical science, every term has to have the same units. Otherwise, it's just nonsense. No units, joules, joules squared. No. So, you divide out by kBT. Remember that kB is the Boltzmann constant. In case you forgot, that is 8.314 joules per k mole. Divided by Avogadro's constant, 6.022. Times temperature. They both have units of energy, so energy over energy, and you're now unitless. And here you go. Okay, so last bit here. So this is the correct way. If you're looking for this vacuum chamber and you want to grab a molecule out of it and say, hey, what's your energy? Is it 1 kilojoule? Then you plug in 1 kilojoule here, and you look at you have to know all the other energies, so you can do this, and that's the probability. That's the probability that when you reach into the vacuum chamber and you grab a molecule, this thing, not terrible, right? This thing tells you the probability that it has 1 kilojoule per mole. Okay, so anyway, next time what we're going to do, by the way, we're going to plug that in. We're going to plug that in, make it simpler, and then apply it towards figuring out what the average speed of a molecule is. And I'll end with this. And here's a cool, I remember you have a homework cover. Here's a cool thing. Who believes that molecules move faster than the speed of sound? What do you think? The answer is most gas molecules in the air move faster than the speed of sound. I don't understand that either, but it's true. We're going to